Okay, we'll continue on in chapter 4, and our topic today is linear regression. And the idea behind linear regression is we want to create a mathematical model to describe the relationship between two numeric variables. Okay, so okay, or in essence, we can just think of it as we want the equation of the trend line. Okay. So, let's say you have some data like this, and you're going to fit it with some kind of trend line here. Okay, so who knows? Maybe this is the trend line, and we want to know what is this equation. Okay, what is the equation of this line? Okay, the trend line, or our what we call our best fit line, shows what we would predict y to be for a particular value of x. Okay, so if you plug in an x right here, you go up to the line, and this is your spot right there. And we'd say, for this value of x, we predict the y to be right here. Okay, so for this value, this x, we predict y is here. And because the equation is a straight line, we would say y, and we put a little hat over this. This is called y hat. This represents the prediction of y, represents our prediction. Okay, and it's a line. So what is the equation of a line? Okay, so you learned probably in algebra of the line is y equals mx plus b. In statistics, we change up the letters, and we have a plus bx. Okay, and now this is our intercept, and this is our slope. And this, on this hand, we just have the equation of our prediction line. And that's essentially what we are doing with linear regression. We are just trying to find, we're going to find this equation, okay? And in your lab, the lab this week, did you guys already do it yesterday? Yeah? Okay. So the lab should have shown that the way we fit our best fit line is that it is the line that minimizes the squares of the residual, okay? So the lab should show that the best fit line okay. So a residual is the difference between the actual value of y and what we predict for it. Okay, so for this particular x, we would predict our value of y to be right here at the line, but the actual value, so this up here is our prediction, this down here is the actual. So this difference here, this distance between the prediction and the actual, that is our residual. Okay. And what the best fit line does is it takes each of these residuals and it turns it into a square, and then you find the residuals for every single dot, okay, and you square them all, and the line that minimizes the squares of all of these residuals is the best fit line. Okay, and I'm hoping in the lab you explored this, or you'll explore it when you do it. You'll see that you can adjust all of these things, and the squares change sizes as you fit different lines, and the line that minimizes the squares is the best fit line. Okay, so maybe we'll say the residual is equal to the actual value minus the predicted value. Okay. So the line that minimizes all of these squares, that is the best fit line. Yes, question?
Why do you use the squares instead of just the residual?
Well, there's a few properties of squares, okay, and a lot, so when you have just the residuals, you'll have both positive and negative values, okay, and so and it turns out that when you do it, you're often going to get 0 as a sum of your residuals, okay, for a lot of different things. So you can say, well, we want the line that minimizes the absolute values of the residuals. That's another option, okay? But the problem with dealing with absolute values, if you've taken calculus, is that you have a non-differentiable point at 0. You get this sharp v, okay? And so that causes problems. When you deal with squares, it has a similar property of turning everything positive, much like an absolute value, but it's smoothly differentiable at all points, okay? So it's probably more detail than you guys wanted to know, but that's the answer to the question. So, okay, so this is what we have. All right, and so thanks to the work of other mathematicians or statisticians, we have found the property of the best fit line will always have a certain slope and will always have a certain intercept. Okay, so the will always have the slope. Okay, so the symbol for slope is b, and the slope will always be r times sy over sx. Okay, and the intercept, a, will always be y bar minus b times x bar. Okay. So to find your slope and intercept, you need 5 statistics. From your data, okay? And those are x bar, which is the mean of x, and S sub x, this is the standard deviation of x. You need y bar, this is the mean of y, sy, and this is the standard deviation of y. Okay, and if you had to, you could calculate the mean of x and the standard deviation of x if I were to give you a data set, right? It might be a little tedious if you have like 7 data points or more than that, calculating the standard deviation and things. That would involve a lot of number crunching, but if you had to calculate that, you could do it. Okay, all you do is you take the mean of the column of x values, the standard deviation of the column of x values. Okay, and then the last one we need is the correlation between x and y. And we did not cover how to calculate the correlation between x and y by hand, and we will not do that, and that's okay. Okay, because we have computers and that they do our work for us. Okay, so you can assume R will that R will be provided for you. All right, so let's try out an example here. Okay. And what we are doing is we are going to we're going to take a look at some books. Okay. Okay, and we look at how many pages are in the book. Ooh. And based on the number of pages, we predict the width or the thickness of the book. Okay. And so now we have to establish what our x variable and what our y variable are. Okay. And so the x variable is often called the predictor variable. It is the variable we use, okay, the variable we use to make predictions. So it is often called our predictor, or it can be called the explanatory variable. And sometimes it's called the independent variable. I don't really like that term, but it does appear in the literature. So I'll put it here. Okay. And the y variable, on the other hand, is the variable that we are predicting. Okay, so this would be the predicted variable. Or the response variable. And again, I don't really like this term, but it might be called the dependent variable. Should I make a clicker question out of this? Sure, we'll give you an easy one. Okay, so we have two variables. One is the pages and one is the width. Okay, so I'm going to ask which is the x variable. A for pages, B for width. Okay, go ahead and click away. Okay, did everyone get their answers in? We'll say just 10 more seconds here. Just click away. So again, x is the one we're using to make predictions. Y is the variable that we are predicting. and it says based on the number of pages, we want to predict the width of the book. So which is the x variable here? Okay, I'm going to hit stop. Okay, and indeed the pages is the x variable, and so the regression equation, the trend line, our regression line will be in the form and so we are predicting width, so it's going to be width, and we put a little hat to indicate that this is what we are predicting, and it's going to be width is A plus B times pages, okay, to indicate that we're plugging in pages to get our width. Okay, so this is our intercept, and here's our slope. Okay, so let's get the actual intercept and slope, and here I'm going to just use some pre-calculated values for us. Okay, so here we've got, I'm going to just throw some dots up on the chart here. Okay, and okay. And so here we're going to say, as far as width goes, it's going to be 6.22 plus 0.0366 pages, okay? So width is measured in millimeters, okay? Okay, and so which value here is our slope? I don't think we need another clicker question for this, right? So our slope is equal to, what do we say? 0.0366, right? This is our slope. That's our A, and our B is our slope. Okay, so let's try this out. Let me give you a little exercise here. I won't bother making a question out of this. Okay, but let's say, if a book has 400 pages in it, what do we predict its width? What do we predict for its width? Okay. And then let me ask another question. It'll be the same question. A book has 500 pages. And we're going to ask predicted width. Okay. All right, so, well, I'll let you guys calculate these out. And just tell me what values you get. Okay. Here we'll do one more. Okay, we'll do and then the book has 600 pages. And what is its predicted width? All right, do we have some values here? Yes? No? Maybe? Okay. So if I plug in, for this first one, I'm going to plug in for pages. Our pages is our x variable. We're going to plug in the value 400 here. Okay? And so my predicted width is going to be 6.22 plus 0.0366 times 400. And if I run that in my calculator, 6.22 plus 0.0366 times 400, okay, it tells me that number is 20.86. Okay, let's do the same thing for 500. So I do x is 500. Okay, I'm just going to write y hat is 6.22 plus 0.0366 times 500. Okay, and so plus 0.0366 times 500, I get 24.52. And doing the same thing, but this time with 600, 28.18, right? All right, is that okay with everybody? Okay, so here's another question. How much did y hat change between 500 and 400? How much did y hat change? So I can do 24.52 minus 20.86, and I see that y hat changed by an additional 3.66. Is that good? Okay. And then how much did y hat change when I went from 500 to 600 pages? Okay, well we can punch this in. 28.18 minus 24.52, also 3.66. Okay, so if the multiplication button on your calculator was broken and I said, can you give me a prediction for a book with 700 pages? You would tell me that book would be what? So its predicted width would be, we could just take 28.18 and add another 3.66, right? We do 28.18 plus 3.66. So my answer there, 31.84. Okay, no multiplication needed. So where is this 3.66 coming from? Yeah, it's coming from our slope, right? If we look at this, this is our slope. So my slope is equal to 0.0366. Okay? My slope is 0.0366. And basically, when I'm adding 100 pages, I'm going to add 100 times the slope. Okay? So with 100 pages, we add 100 times 0.0366, or 3.66. Okay, and so this gives us some insight as to what the slope means. Okay, so the interpretation of the slope this tells us how much we expect y to change if x goes up by 1. Okay? And obviously if x goes up by 100, we expect y to change by 100 times the slope. Okay? And so that's what we can say as far as the interpretation of the slope. So in our case, we said predicted width is 6.22 plus 0.0366 times pages. Our slope is 0.0366, and the interpretation in this context is that if the number of pages in the book goes up by 1, we predict the width to increase 0.0366 millimeters. Okay? So we can think of it as kind of like, you know, the thickness of one page there, okay? Which, you know, these numbers are tiny and it's hard to visualize, so I think it's easier to think of, you know, 100 pages or something like that, okay? It is important to note that we have to use the word predict or how much we expect y to change, okay? It's important that we keep these in here because as far as our, you know, best fit and our trend line goes, these are all about predictions. It doesn't mean that the thickness of the book actually go up by this much. Yeah, question?
So with this question, it was pretty, well, we logically know how the relationship works.
Yes.
But you asked us the clicker question as if from these sort of situations, we can tell which one's the positive, or well, not positive, but it sort of implied that we can tell which one's the positive.
Yeah, so it's all in the way we've phrased the question, okay? So it is technically possible. So in this case, you know, we're counting the number of pages and we're trying to predict the width, okay? Now somebody else could play a different game and say, well, I'm going to take a ruler and I'm going to measure how thick the book is, and based on how wide the book is, I'm going to try to predict how many pages are in the book, okay? And we could play a reverse game like that. In that case, the width would be the x, and then the number of pages, which is what we're predicting, would be the y. Okay, so it's all in the way we phrased. We are going to use this to predict this. Okay, the thing that we are using to make the prediction is the x. The thing that we are predicting is the y. Okay, and it goes either way. It doesn't have to be one causes the other. Okay, and you know, so in this case, it feels like the number of pages causes the width of the book, and that's fine. But there's a lot of situations where you're not quite sure which one is causing the other, and it doesn't really matter. Okay, the one you're using to make predictions is the x. The one you're predicting is the y, and that's always going to be the case, whether it's caused the other way around or not. Okay, so that is the slope. This value 6.22, this is our intercept. The intercept is 6.22, okay? And the meaning of the intercept this is our prediction for y if we can plug in 0 for x. Okay, and I have to say sometimes it makes sense and sometimes it does not. Okay, so could we have a book with 0 pages in it? Maybe, I don't know. I guess you could take your textbook, tear out all the pages, okay, and you'll be left with the covers, all right? And so in this case, it would be, you know, if a book has 0 pages, right? So in our case, our 6.22, the 6.22, it kind of means, you know, if a book has 0 pages, we predict the width to be 6.22 millimeters, okay? On the other hand, we could have something like, we want to predict the weight of the snake based on its length, okay? And so let's say we're going to predict the weight of a snake, based on its length. And I'm just completely making up numbers. I have no idea how much snakes weigh. Right? Okay. I have no idea what units these are in. Okay. But what this means, so here the slope is 16. Okay, and that means if the length goes up by 1 unit, 1 inch, 1 whatever, okay, length goes up by 1 unit, we predict the weight to go up 45. I mean, to go up 16. We predict the weight to go up 16. Okay? As far as our intercept here is 45. And that would be, if we have a snake of length 0, we predict its weight to be 45. And that just doesn't make sense. Okay. So, this is nonsense. Okay? You cannot have a snake of length 0, okay? It's literally not a snake. Okay. So that's that. Okay. As you work with linear regression, we kind of have this thing to try to measure how good our linear regression model is. Okay, and this is called the coefficient of determination. It's a fancy name. Okay. Few people, even few statisticians, refer to it by its full name, the coefficient of determination. We just call it R squared. Okay? And R squared, it's a loose measure to tell us how good our fit is. Okay? How good our fit, how good our fit is. Or another way to think of it is, does the straight line do a pretty good job of explaining the data? Okay. And for linear regression, we might call for simple linear regression, which is what we have just learned. R squared is equal to the quantity R raised to the second power squared. Okay, and that seems to be like a trivial relationship. In higher levels or more complicated regression, this relationship no longer holds. But for simple linear regression, this works. Okay, and thus R squared will be between 0 and 1 inclusive. And the definition of r squared is, this is the amount of variation in y that can be, and I'm going to write, quote, explained by x. Okay? The amount of variation in y that can be, quote, explained by x. All right? Okay, so let me give you a little example to try to make sense of this sentence here, because I know it sounds a little wonky. Okay? So let's say you go to an elementary school, right? Okay, so you visit an elementary school. Okay, and we're going to look at, we're interested in the heights of the different kids. Okay, so we observe the different heights of kids. Okay, so we'll say our heights will be y. Okay, so y is equal to height. Okay, and when you go to the elementary school, all right, you go, just imagine you're completely naive to everything, right? You show up at this elementary school, you go, wow, there's a lot of kids, and you go, wow, some are tall and some are short. Okay, you go, wow, there's a wide range of heights here. Okay, there's a lot of variation here. I wonder why some kids are tall and some kids are short. Okay, and so you say, oh, well, somebody comes to you and then you say, well, can you explain to me why some kids are tall and some kids are short at this elementary school? And we can say, you know, there's a lot of things that determine how tall or how short a child is, okay? There are things like diet and genetics and all of this. But probably the most important thing that explains the different heights as far as the elementary school goes is that the kids are different ages, right? And so it probably makes sense to say, well, let's take a look at the age of kids and see if that explains a lot of the reason why kids are of different heights, okay? And so if we do this, you know, we can plot age over here. We can say x is equal to age, y is height, and at the elementary school we would see probably a near linear relationship between age and height, something like this. Okay, and okay, and so, you know, r might be, let's say, 0.85, okay, and then so my r squared would be 0.85 squared. I don't know what that is. Let me see, 72225? Yeah, okay. 0.7225, right? Okay. So here, my r squared says 72% of the variation in height can be explained by age. 72.25% of the variation in height can be explained by age. And what that means is that if you look at these children and they have different heights, sure, age can explain a lot of the reason why some kids are taller than others. Okay, you look at the 6th graders, they're taller than the 1st graders, and that's because of age. However, if you look at the 6th graders, you have a bunch of students that are all the same age, you're still going to have tall and short kids within 6th grade. And so basically the remaining 27% or so is explained by different factors, such as diet and genetics and gender and all of this stuff. Okay, all of these other things go into determining someone's height. And so what r squared does is it says if age is the only thing that we're looking at, r squared says age explains about 72.25% of the variation in y. The rest of that variation, the rest of the reason why some kids are tall and some kids are short. Those come from different reasons, okay? And so that is that's the meaning of r squared there. All right, let's try just a quick little question here, okay? All right, so let's say you you have a plot of data, and it looks like this, okay? So you've got a nice linear relationship, okay? So you have a linear relationship. And then, so you perform regression. And you find, as far as y and x goes, that 49% of the variation in y can be explained by x. Okay, so based on this, tell me, what is the value of the correlation? Okay, and so here are your choices. Okay, A will be 0.51, B is 0.49, C is 0.7, and D is negative 0.7. Okay. Okay, you can discuss with your neighbors what you think the answer should be. Let me just pause the video here. Okay, let's take a look, and the answer is D. Okay, so what's going on here? So 49% of the variation can be explained by x. This tells us that r squared is equal to 0.49, okay? And we know that when we take r and we square it, we would get r squared. So therefore, r is equal to the square root of 0.49, which gives us plus or minus 0.7. Now we look at our picture, and we know that the correlation has to be negative, okay? So we have a negative relationship. So that means the correlation must be negative 0.7 and not positive 0.7, okay? Both correlation 0.7 and negative 0.7 would give me an r squared of 0.49, and this sentence would be true. But when we look at our plot, we can see that there is a negative relationship, and therefore our correlation must be negative 0.7. Okay, I'm going to give you some warnings about linear regression, and we might run out of time here before I get to cover all of them, but we'll start here, and then and if I have to use a little bit of class time on Monday to finish out the warnings, I think that's okay. All right, so some warnings. Linear regression is a very powerful tool. It's very useful, but you can get in some trouble here. Okay, so first of all, x and y must have a linear relationship. Okay. Okay, you can't just calculate correlation and calculate those other summary statistics and get a linear regression line. So x and y must have a linear relationship, otherwise it will not make sense. Okay, otherwise the model does not make sense. we have situations where beware of outliers, as they can greatly affect your analysis. Okay. All right, and so let's say we are looking at shoe size and income. Okay, so if we just take out the normal population, we would probably see no real correlation between shoe size and income. Okay, so R should probably be 0 for the normal population. Okay, what if in your sample you ended up getting Shaquille O'Neal? Okay, Shaquille O'Neal has huge feet and he has a very high income. Okay, so he's going to be an outlier, like right here. Okay, this is Shaq. Okay, and so now if you so the original trend line should show kind of this flat thing, no relationship. Whoops. But then now with Shaquille O'Neal in here, the trend line is going to try to accommodate Shaq, and then so now it would seem like there is a relationship. Okay, so that's no good. Okay, so this is the original, and then this is with Shaq. Okay, so you gotta watch out for that. So so that's no good. Okay, and then another warning is do not extrapolate to where you have not collected data. Okay, so again, let's imagine you've gone to the elementary school. Okay, maybe you're an alien from another planet. You've gone to the elementary school, and you look at the age of kids and their heights. Okay, and it seems every year at the elementary school, you know, ages 5, 6, 7, 8, 9, 10, 11, every year the kids get taller and taller and taller. Okay, well, you might be tempted to extrapolate and say, okay, well, by the time these people turn 40 years old, they're going to be 15 feet tall. Okay, and of course that does not make sense, right? So this is where we have collected data up to here. We have data here. Oops. And then out here we have no data. Okay, so as far as the trend line goes, we don't know if it continues or if it goes down or if it rockets up. Okay, we do not know what will happen. Okay, we'll end there, and we'll see you guys on Monday. Have a great weekend.